Today's lesson is section 6.1 and it's graphing systems of equations. So we have a couple definitions to get through today, so let's go ahead and get started. First of all, system of equations is two or more equations that are written together. And today, since we're graphing, we're going to be graphing them together. So if you remember back to chapter 4 when we first learned how to graph equations, it's just like that, except we're going to graph two on the same coordinate plane. Now, the solution to a system of equations is an ordered pair. It's a little thick. All right, so an ordered pair that satisfies both equations. So that's what it is algebraically, but if we look at it graphically, it's the point where our two lines intersect. If we have two lines, remember, they intersect at a point, and that point's an ordered pair, an x value and a y value, and that's the solution to the system of equations. So the graph in this case is going to be like our work to get that ordered pair. Each system is either consistent or inconsistent, and then either independent or dependent. So a consistent system is a system if the lines intersect or have at least one ordered pair. So pretty much if it has a solution, it is consistent. Inconsistent is when there are no ordered pairs that would satisfy both equations, in sense, which means they do not touch ever. So if they do not touch, that means those are parallel lines because they never intersect. So consistent means we get a solution. So algebraically, that ordered pair, if we were to substitute that ordered pair, x, y, back into both equations, we would get two true statements. However, if we substitute that ordered pair back in and it does not work for either of them, it's inconsistent. If it works for one of them but not both, it is also inconsistent because in order for it to be a solution, it has to work for both. It's independent if it has only one solution. And if it has infinitely many solutions, it's dependent. And we're going to see in just a moment what that looks like when it's dependent and has many solutions. So let's look at this key concept box. So first of all, the graph. It has two equations, or two graphs, two lines. So it has exactly one solution because it intersects at one point. We'll say that point right there, which means it's consistent and independent. The second one, it looks like we only have one equation, just one. But really that equation could be y equals 2x plus 1. But another equation could be 2y equals 4x plus 2. If we were to simplify this second equation, it would give us the first. So really it appears that we have two separate equations, but when we graph them, it ends up being the same line. So when that happens, that's how we actually get infinitely many solutions. Because if I have one line on top of another one, they are intersecting at every single point. When that happens, it's consistent and dependent. And finally, when we have two parallel lines never intersect. And if our solution is the intersection point and they never intersect, that means we get no solution and it is inconsistent. Let's take a look at our first example. It says use each graph to determine whether the solution has no solution, one solution, or many solutions. So if we look at our first one, we have y equals negative x plus 1 and y equals negative x plus 4. They have labeled each line for us, but we can tell the difference because negative x plus 1, well, that one intersects right there at 1 on the y-axis, and negative x plus 4 intersects at 4 on the y-axis. So when we look at those two, we can see that those two never touch. So that means it has no solution. And we can go a step further and say that it's inconsistent. Okay. Now taking a look at part B, we have two lines. We can see them here. Now if you notice this line that I'm about to highlight, it has two separate equations on it. But if you look, it's actually the same equation. If I take 3x minus 3 equals 9 and divide everything by 3, we get x minus y equals 3. So that's another way how they can look different, but they're actually the same equation. So if I look at these two, hey, they actually intersect. So that means we get one solution. I'm going to have us name this so we can get practice with it. So that solution is that point right there where they intersect. So that solution is 2, -1. And if we get one solution, we know it's consistent and independent. All right, so you guys have a couple your turns to try. So go ahead, try those, and then we'll come back together. And one thing I will tell you, let's see if I can get a black one. This is missing the 3 in front of the x. That might help you a little bit. Now I'm seeing something, an equation that I do not see there, so I'm going to go ahead and solve this for y and see if that helps. Oh my goodness, that equation was there. Oh, but that top one was not there. So this is the same as that, so that's going to be my green one, which started out as this one. Now I have my 2x plus 3 equals 6. Oh, that's the same equation. So we get many solutions. And technically it is infinitely many because the line goes on forever. We just usually write many solutions. All right, example 2. Here's where we get into the fun. We get to graph these. Now, one thing I will tell you, especially if you're using your iPad to write on this, 2 colors, no problem, because we have a whole bunch of colors, and we can even get more if we want. But if we were in the classroom, I would have passed out 2 pencils today, 2 colored pencils, or asked you to get 2 colors out, just to help us keep our work organized. So my first equation is going to be in the pink color. So I'm going to get 2x minus y equals 3. Now I need to solve this for y so that I can graph it. So don't forget that negative in front of the y. I'm going to move my 2x over by subtracting it. So minus 2x plus 3. And now I need to divide everything by that -1. So y equals -2 divided by -1 is a positive 2x. And my positive 3 becomes a minus 3. So now we are just going to graph this using our slope and our y-intercept. So the y-intercept is -3. And notice how I'm doing this all in the same color. That way I know the work goes along with my pink equation. So the pink work goes along with the pink equation. And now up 2 over 1. And keep going. Now this is not like the last graphs we graphed. This is always a solid line because it's an equal sign, and we do not have to shade for this. All right, now I will tell you, this is one thing that it might be very helpful if you're doing this on, like if you printed out the notes and you're doing this on a piece of paper, you might want to get a ruler. We want to be as accurate as possible. If our line is not very accurate, that's going to make my intersection point off. So we really have to be as accurate as possible, which we're going to find out in this chapter the graphing systems of equations, like to find the solution, the graphing is actually the least accurate method because of that fact. All right, so I'm gonna get my other color. We'll do dark green. So then I like to put this up here, that way I remember. And now I need to solve this one for y as well. So 8x minus 4y equals negative 12. So negative 4y equals negative x minus 12, and divide everything by negative 4. So negative divided by negative is a positive. 8 divided by 4 is 2x plus 3. So now I'm going to go up 3, put my dot, and now my slope is up 2 over 1. I can only go 1 there, so I have to go down 2, back 1. I don't know if any of you noticed, but we can actually tell by those two equations what's going to happen with our graph. So there's my two lines. I've graphed them, and now it's showing that they're parallel. Okay, it's showing that my two lines are parallel. So parallel means we have no solution. No solution. All right, and if you were wondering how I knew that just by looking at them, so I looked at their slopes, and they're the same slope. So same slope means I'm going to get two parallel lines. Or it could also be the same line. So we need to look at the y-intercepts then. Well, this y-intercept is negative 3. This one is positive 3. So since I have the same slope, but two different y-intercepts, that means I have two different lines that are going to be parallel. Okay? If we had the same slope and the same y-intercept, that would have been one equation, which would have been many solutions. All right, now taking a look at part B. My first one, let's get a bright color. Oh, we'll do orange today. Again, we have to go through and solve this for y. Some of them are already solved for y, and that makes your life just a little bit easier. All right, so I'm going to subtract x from both sides. So negative 2y equals negative x plus 4. And now I'm going to divide both sides by 2, negative 2. I'll show that. Sorry, I didn't show that on the last problem. So y equals 1/2 x, and that's positive, minus 2. So I'm going to go down 2 and put a dot. And now my slope is up 1 for the rise, over 2 for the run. So up 1 over 2. Down 1 to the left 2. All right, so there's that line. Again, try to make it as accurate as possible. All right, let's do this rainbow color. For my next equation, it is, oh, I don't know if that's going to work out too well. Let's try this again. So we're going to get x minus 2y equals negative 2. So I'm going to subtract x from both sides. Divide everything by negative 2. So we get y equals 1/2 x. Negative divided by negative is a positive 1. So now I have to go up 1 and put a dot. And then slope is up 1 to the right 2. And I can go down 1 to the left 2. Let me make my line. If you don't have more than one color, also what you could do, so say we just had this pencil. I could say, hey, this is line 1, that is line 2, and then I could say, hey, this one's line 1, and that is line 2. This is the work for 1, that is the work for 2, and that way it helps you keep everything organized. The reason to do that is if you look at your graphs and they're incorrect, you don't have to guess, all right, oh no, which work did I make a mistake on? You know exactly which one. All right. So going back to this, we have, again, no solution. I promise they're not all no solution. No solution because they are parallel. Double check. Yep, slopes are the same. Y-intercepts are 0. All right, you guys have 2 to do, and then your notes are done for today. So pause the video, try those 2 your turns on your own, then come back and check. Oh, we got lucky on this one. This one's already solved for y. All right, so this one we actually get a solution. So we're going to write one solution. And if you look at the directions, if the system has one solution, we need to name it. So this solution, let me get my highlighter, is right there. So that's, whoops, didn't want to touch it. That's 0, 1, 2, 3. So that's my answer. One solution, and that solution is at 0, 3. So what that means, and we'll go ahead and do it, if I substitute 0, 3 into both of those equations, we're going to get 2 true answers. So I'm going to get 3 equals 2 times 0 plus 3. So let's see. 3 equals 0 plus 3. 3 equals 3. Amazing. Now the next one, 3 equals 1/2 times 0 plus 3. 3 equals 0 plus 3. 3 is equal to 3. Works out again. Okay, you have one more to do. This one's going to require us to solve for y. Now for this one, I'm just rewriting this for the y-intercept to make it a little bit easier for us to find. So 1 1/3 is approximately right there. And do you see why this is sort of like an estimate to give us our answer? So now I have to go down 1 unit from there. So that's right there, and then over 3 to the right. Now I have to go up 1 unit approximately, which is right there. I erase all those, and then back 3. Let me erase all these other little points. All right, so there's our equation. That's sort of an estimate because, there we go. Now the second one, we have to solve it again. Oh, so don't forget that plus 0 just means it crosses right at the origin. And then down 1 over 3. Up 1 to the left 3. Don't forget that negative slope should go down from left to right. And if we look, those two are parallel, so we get no solution.